Number 8, we've got a solid metallic sphere of radius r. It has charge positive 2q, and a hollow sphere with radius 3r, negative q. In the first part, we have to draw a diagram showing the electric field lines in all regions inside and outside of the sphere. So what we're going to do is focus on the positive 2q, and since there are, I'm going to work with this simple concept as possible. Since there are two, I'm just going to show that because it's positive, electric field lines go out, and so they should go out in this direction as well. And again, the outer shell does not stop the electric field from going through. The negative Q, actually, let me double it just because it just gives better effect. Okay, then the fact that the outer shell has negative Q means that we need half of the electric field lines. And when we're focused on a conductor, the conductor is only going to have an electric field on the outside of its surface, not on the inside. We call this a Faraday's cage. So for the negative Q, I'm going to do that in a different color. For the negative Q, we want to show electric field lines going into the shell, but only from the outside. So if I had 4 for the 2Q, I should have 2 for the negative Q. I'm not going to draw electric field lines going into the shell from the inside because keep in mind a hollow or any sort of conducting surface is a hollow conducting surface is going to create Faraday's cage where the electric field created by that charged surface is going to be eliminated. And then this technically isn't wrong, but in general, you would draw the net electric field, meaning that if you had some positive charges canceling out with negative charges, or if they're opposing direction, equal and opposite, then you would cancel those out. So in the end, all this would be eliminated, and you would have 4 electric field lines going out and 2 electric field lines going out left from the negative Q charge of the shell. Okay, next step is to use Gauss's law to determine the magnitude of the electric field between region R and 3R. So what we are again focused on is we've got positive 2Q and we've got negative Q on the outside. Since we are working with this region, we only need to focus on the enclosed charge. So our E 4 pi r squared is equal to the 2Q of the charge over epsilon naught. And then you can simplify this out to E is equal to Q over 2 pi r squared epsilon naught. But a lot of the time, it's easier to work with this equation. K, let me pull the 2 out in front. Q over epsilon naught. And those two mean the same thing. Okay, next up, find the potential difference between the sphere and the shell. So the potential difference, this is part C, is our equation negative integral from, and when we're working with spheres, we always go from the outer shell, 3R, to the inner shell. And then our equation is, I like this guy, much easier to work with. Oops, I messed up my equation here. The epsilon naught was part of the K. I forgot to put the R squared. So hopefully I didn't confuse you there. because it's hard to take the integral with respect to dr if I don't have an r. So this is my equation. I'm going to pull out my constants and integrate from 3r to r. R to the negative 2 is the same as 1 over r squared. And then I end up getting negative 1 over r from big R to 3r. The negatives cancel out, and I get 2kq 1 over r minus 1 over 3r. And if I put common denominators in here, I end up with 2kq 2 over 3r, or 4kq over 3r. That one was part C. Again, you can simplify this to the answer in the answer key if you substitute 1 over 4 pi epsilon naught in for k. And then for D, this is a good conceptual question. What would be the final distribution of the charge if the spheres were connected with a conducting wire? A conducting wire means that the charges from the 2q, let me go up here, the charges from this 2q can flow out to the charges in the spherical surface. So what we want to think about is conservation of charge means that the net charge for the sphere and the shell is going to be positive 2q minus q, which is just positive q. That extra net charge of positive q is going to want to get away from each other as much as possible, and the furthest place they can go is right on the surface. So how are the charges distributed? The sphere would end up neutral, and then the excess charge of positive q would be on the shell charged negative q. Or was it negative? It was positive q.